So, you would like to add touch buttons to your Arduino project, but you don't want to pay for it? That is a fantastic idea. After this video, you will know how to do it. This kind of touch button needs no extra cap sensing chip, uses only standard Arduino functions. It is physically very easy to make, and the response time is super fast. And the best part is, it only takes a few lines of code to implement. We will talk about the physical construction of the touch button, how it works, and walk through the Arduino code. Let's get started. Let's talk about the physical construction of the button. On the front side of the button is simply drawn onto the plastic with a marker pen. That's it. Now let's flip it back. On the back side, what you have is a piece of copper foil tape secured to the plastic with generous amount of hot glue. And that's it. Simple as that. You do need to solder a wire to the copper foil tape. My recommendation is that you do the soldering before you apply the hot glue. Alright, now let's talk about how this thing works. To implement this touch button, you will need two pins. The first pin is called the exciter pin. And this pin needs to have the function of digital output, which is essentially every GPIO that you have on your Arduino. The second pin is the cap sense pin. This pin needs two functions. One is digital output, the other is ADC input. And between these two pins, we connect a capacitor of roughly 20 picofarad. You can buy this capacitor for about 1 cent from all the retailers out there. You then connect the cap sense pin to this piece of copper foil behind a piece of plastic. Now between the cap sense pin and ground, there is this phantom capacitor or parasitic capacitor. It includes all the capacitances from all the wires, all the traces, and also the capacitance of the ADC inside the chip. And when you push on this piece of plastic here, like that, this phantom capacitor value will increase. And that is what you are sensing. In my experience, the phantom capacitor increase caused by this finger pushing here is anywhere between 50 femtofarad and 1 picofarad. So how exactly do we measure that capacitance change? Let's go to the next slide. We measure the capacitance change with this three-phase methodology. The first phase is called reset phase. During this reset phase, both the exciter pin and cap sense pin are configured as digital output, and they both output digital low. So during the reset phase, these two voltages are both pulled to ground. And then we enter the pull-up phase, the second phase. During this phase, the exciter pin is still digital output, and it's being pulled to VDD from here to here. The cap sense pin is configured as a ADC input at the beginning of the second phase. And as the exciter pin is being pulled up from ground to VDD, the cap sense pin is also going up, but at a slower pace. This is because these two capacitances, this 1 cent 20 picofarad capacitor and this parasitic capacitor, they kind of form a voltage divider. So when the exciter pin goes all the way to VDD, the cap sense pin here goes to some value lower than VDD. In the third phase, which is the measurement phase, the ADC does its job and tell us what the final value is at the cap sense pin. The final voltage value of the cap sense pin can be expressed by this equation here. When your finger lands on the touch button, the parasitic capacitor CP will increase and the measured voltage will go lower. It should be noted that multiple buttons can share the same exciter pin. For example, here we're implementing two buttons, button 1 and button 2. They share the same exciter pin, which is A0 here on this Arduino Nano. And A1 serves as the cap sense pin for button 1. And A4 serves as the cap sense pin for button 2. If you actually implement this, this is what it looks like. This is button 1. It travels through the green wire and it controls the green LED. Its signal value is displayed on this LCD screen. And this is button 2. It travels through the red wire and controls the red LED. Please note that button 2's signal level is not displayed on the LCD. Now, according to what is predicted by this equation here, when you put your finger on the button, the measured voltage should go down. Let's go see if that's true. Just as predicted, the signal goes down when you push the button. The red line here is the threshold. When the signal falls below the threshold, the button is considered to be pushed and the LED is turned on. All of this is done in the code, which we are going to walk through shortly. But before that, let's talk about a few potential pitfalls. The first potential pitfall is that if you leave any air gap between the plastic and the copper foil here, your signal level will decrease dramatically. Make sure you have very good contact between the copper foil and the plastic. Usually the copper foil tape that you buy comes with adhesive. If it doesn't, you need to use double-sided tape to tape the foil to the plastic. The key is no air gap is allowed. The second pitfall is that you need to be aware of the interference between buttons, and you need to set your threshold accordingly. If you look carefully, you'll see that when you push button 2, button 1 signal actually goes down a little bit. If your threshold is set too high, then sometimes when you're pushing button 2, button 1 will be considered to be pushed by the code. You probably don't want that. Potential pitfall number 3 is touching the wires has the same effect as touching the buttons. This is a physical phenomenon that you cannot get away from. So you probably want to pay attention to how you run your wires in your project to avoid unwanted button touches. Now let's walk through the Arduino code. This is the function that does the cap sensing. It has two inputs, the exciter pin and the sense pin, essentially just specifying which pins to use. These 4 lines are for phase 1. During phase 1, which is the reset phase, both pins are set to low or ground, as shown in this graph. And these 3 lines are for phase 2. In the beginning of phase 2, the sense pin is changed from output to input. And then the exciter pin is set to high, as shown here in this graph. And then we put in a delay of 5 microseconds just to be safe. This provides plenty of time for the voltages to settle completely. And these few lines are for phase 3, which is the measurement phase. In the beginning of the measurement phase, we issue the read command to the ADC and get the sense pin voltage value. After that, we need to set the sense pin back to output. This is to prevent excessive inter-button interference that we showed before. This whole function takes roughly 140 microseconds to execute, which means every second you get to have 7,000 reads, which is fast enough for most applications. If you find your touch buttons to be quite noisy, then what you can do is to use this function to perform an average read. What this function does is simply to call this cap sensor function many times and take the output's average to reduce the output noise at the expense of a slower read. For example, if you use this function to take 64 samples and take the average of those 64 samples, your noise level will be reduced by a factor of 8 and your read speed will be reduced by a factor of 64. The output of these functions is an ADC code that corresponds to the voltage value. You still need to compare that voltage value with the threshold to get a binary output. For example, these 4 lines implement the binary output of button 2. First, this averaged cap sensor function is called. If the result is less than button 2 threshold, B2 thresh means button 2 threshold, then the button 2 LED is set to be high. Otherwise, it's set to low. So that was everything you need to know to build touch buttons for free for your Arduino project. Hopefully, it has been useful for you. See you next time.